Let S be a non-empty set and V a vector space. Let V power S denote the set of functions from S to V. Define a natural addition and scalar multiplication on V power S. Show that with these operations, the set V power S becomes a vector space. V is a vector space over F. We will show that V power S is also a vector space over F. For instance, given functions f and g from S to V, we have to define f plus g as a function. Likewise, given a scalar lambda and a function f from S to V, we have to define lambda times f as a function. The natural definitions are as follows, where the operation on the right-hand side of the definition occurs in V. These are valid definitions of addition and scalar multiplication in the set V power S. What remains to be done is to show that these operations on the set V power S in fact satisfy the requirements for a vector space. All these properties on the operations just defined on V power S are proved using the fact that they are true on the vector space V. We will show some of them and leave others as exercise, since they are very similar. For commutativity, we have to show that given any two functions f and g from S to V, f plus g equals g plus f. By definition of the addition operation, this means that for every x in S, fx plus gx equals gx plus fx, which is true by the commutativity of the addition in the vector space V. In a similar way, show associativity of the addition and of the scalar multiplication. This will require using the definitions of addition and scalar multiplication twice, each. Now for the additive identity, we have to show that V power S has an element acting as 0 with respect to addition. We first have to define what this element is as a function from S to V. The natural choice is the constant function 0. It's important to notice that on the left-hand side, 0 is the function 0, an element of V power S, while 0 on the right-hand side is the 0 in V. We still have to show that this element in V power S indeed has the desired property. This is equivalent to showing that for any x in S, f plus 0 at x is equal to f at x, which by definition of addition means that for any x in S, f at x plus 0 at x is equal to f at x. And by the definition of zero function, this means that for any x, f at x plus 0 is equal to f at x. But this is true by the additive identity property in the vector space V. Another property that needs proof is the additive inverse. Now, given an element f in V power s, one needs to define minus f. The verification that this satisfies the desired property is left as exercise. For the multiplicative identity, show that the scalar multiplication by 1 leaves every element in V power s unchanged. This follows from the scalar multiplication defined in V power s and the multiplicative identity property in V. For the distributive property, there are two formulas to prove. We verify one and leave the other one as exercise. This requires to prove that the two functions at each side of the equation are equal, which can be proved showing they are equal at every x in S. Again, using the definitions of addition and scalar multiplication in V power s, this can be reduced to the following equation. This is true thanks to the distributive property in V.